the treatment effect on the 5-year mortality rate was more than 30% reduction compared to the baseline level. So then from this single clinical trial alone, the lives and deaths of hundreds of individuals depends on how to design this clinical trial and who gets which treatment. Then this motivates me to think about the problem of welfare in the design of RCTs. Then I'm going to use the following stylized framework where we have a bunch of experimental subjects, I1 to IN, to be assigned to a bunch of experimental treatments from T0 to Tn. Okay. Then I assume that the experimenter has a couple of measurements about subjects' predicted welfare. A key measurement about subject welfare is probably some information about how effective each treatment is likely to be for different types of experimental subjects. And I'm going to use this ETI symbol to denote this predicted effect of each treatment T on each subject I. And these predicted effects are supposed to be coming from prior experiments or observational studies, as is sort of always done in medical and business domains. Then even conditional on these predicted effects as a first welfare measure, there is ample evidence that different subjects have different preferences about what kind of treatments they want. And to capture this preference aspect of subject welfare, I'm going to use this WIT to denote each subject I's willingness to pay, or WTP, for each treatment T. So W and E are going to be my sort of prior welfare measures. And I'm going to use this first treatment T0 to denote a control or placebo to be compared to other things. And let's normalize both E and W, so that both E and W are 0 for this control. So everything is going to be measured relative to this control thing. Okay, so then that's the framework. And any question or clarification? Good. Then given this, different experimental designs produce different treatment assignment probabilities. Okay. The benchmark experimental design is the usual RCT, which assigns each subject to each treatment, with some constant assignment probability denoted by this P super RCT. And I'm going to denote this PRCT as the ratio of each treatment T's pseudo or quasi-capacity CT relative to the total number of experimental subjects N. Now from this expression alone, it should be clear that this RCT doesn't directly incorporate any information about willingness to pay W and the predicted effects E. So my first theoretical question is how to sort of incorporate this additional rich data about subject welfare, especially willingness to pay and predicted effects. And to answer this question, I'm going to develop and consider the following experimental design, which I'm going to call experiment as market, or in short, exam. So this exam is an application of microeconomics or market and mechanism design to this experimental design program. So at a high level, let's create a completely hypothetical centralized market economy in the experimental's computer. And in this market economy, commodities or goods to be allocated correspond to treatment assignment probabilities. And consumers correspond to experimental subjects. Then let's substitute the experimental's data into this economy to compute the resulting competitive market equilibrium allocation of treatment assignment probabilities. So my proposal is to use this competitive market equilibrium as a possible experimental design. More specifically, let's find any personalized price competitive market equilibrium, which is defined as a combination of feasible treatment assignment probabilities P star, as well as their prices pi with a few equilibrium restriction. So the formal definition is slightly complicated. So let me go through these pieces one by one. So first of all, this pi TE object, this red object, is the price of 1 unit of assignment probability at treatment T for experimental subjects for whom the predicted effect of this treatment T is given by E. here, so E is just some number or some potential level of treatment. Then I'm going to require this pi TE to be written as in this equation with some negative weight alpha on the predicted effect level. So the idea behind this negative weight alpha is that each treatment should be cheaper for experimental subjects who are more likely to be benefiting from this specific treatment T. Okay, some effectiveness-based price personalization or price discrimination going on. Then, given these personalized prices, each subject is going to solve a constraint utility maximization problem. Specifically, this P star IT, okay, is the probability that subject I is assigned to treatment T. Then for each subject I, I'm going to require the combination of the vector of treatment assignment probabilities to the solution to the utility maximization problem, okay, in the middle on the right-hand side. So in this utility maximization problem, okay, each person is trying to maximize the expected willingness to pay for assigned treatment, okay, but subjected to some budget constraint. And the budget constraint is formed by the personalized prices coming from the first step, as well as a common budget B, the blue object. And this blue object, the common budget, is picked by the experimenter as some sort of constant number, okay, which is the same for every subject. Then finally, I also require some innocuous capacity constraints. Okay. Then let's find any treatment assignment probabilities P star that satisfy all of these equilibrium conditions. Then for those who are sort of familiar to mechanism design, this is clearly a version or an extension of the very classic idea in economics and mechanism design, that is competitive market equilibrium from equal incomes, which has a very long history, at least since 1960s. And from the purely sort of economic or mechanism design perspective, this is the end of the story. But from the experimental design perspective, there remains some problem. That is, this assignment probability P star may be equal to 0 or 1, so that there will be no randomization anymore. So to deal with this problem, design of exam. So my preferred answer is that this exam has a particular welfare optimality property in the spirit of the first fundamental theorem of welfare economics. What I mean by that is that exam, okay, optimally randomly assigns each treatment to subjects with better predicted effects of that treatment, or to subjects with higher willingness to pay for that treatment. More precisely, for any feasible choice of the epsilon parameter, there always exists a combination of assignment probabilities that satisfies all of the exam conditions. So some equilibrium existence result. Then for any such assignment probabilities in exam, it is ex ante Pareto optimal in the following sense. That is, there is no alternative experimental design P without a star, okay, with the same random assignment condition such that the alternative design, Pareto dominates exam in terms of these two welfare measures listed here. The expected willingness to pay for assigned treatment and the expected predicted effect of assigned treatment. So therefore, as long as the experimenter cares about these two things, the expected willingness to pay and the expected predicted effect, there is no alternative experimental design that is clearly better than exam from the ex ante perspective. So in this sense, exam has the good welfare optimality property. Then in this result, I take this willingness to pay data W as given and as representing the true preferences of experimental subjects, right? But in practice, these preferences and willingness to pay are, of course, private information, okay, held by experimental subjects themselves. So therefore, in practice, the experimenter needs to ask experimental subjects to report their preferences about different types of treatments, right? And in this sort of preference reporting or willingness to pay reporting process, one concern is incentive compatibility. That is, whether subjects find it sort of optimal and makes sense to simply report the true willingness to pay to the experimenter. And the theoretical answer to this question turns out to be yes, in the sense that exam can be shown to be incentive compatible for willingness to pay reporting, at least for large enough experimental design problems. So it is almost always optimal for experimental subjects to report the true willingness to pay to the experimenter when experimental subjects are trying to maximize, the private benefit coming from that willingness to pay reporting. So in this sense, exam is welfare optimal in an incentive compatible way. Then the final methodological question is probably what about information, right? That is, since this is an experimental design, we'd like to use the resulting data coming from this exam experimental design to estimate treatment effects and policy effects. Then to provide an answer to this question, suppose that the experimenter cares about the causal effect of each treatment on some outcome yi, which is the observed outcome for each subject I. Okay? Then I use this usual yi of t symbol to denote subject i's potential outcome when subject I is hypothetically assigned to a particular treatment t. Okay? Then, of course, many of these potential outcomes are simply unobserved, so that the experimenter wants to estimate or learn a certain parameter of this unknown distribution of potential outcomes. And let's denote that parameter of interest by theta. Okay, one possible example of theta is the average treatment effect for this population of experimental subjects. Then finally, I'm going to use this WBIT to denote the indicator that subject I is assigned to treatment T. Okay? Then with these pieces of notation at hand, I'm going to say that this parameter theta is unbiasedly estimable with any given experimental design P, okay, if the following is true. That is, there is some estimator theta hat, okay, which is a function only of observed outcomes and observed treatment assignments, such that this estimator is unbiased for this parameter theta when the data generating process is given by this experimental design P. And it turns out that whenever some parameter theta is unbiasedly estimable with RCT, this same parameter is also unbiasedly estimable with exam with any positive choice of the epsilon parameter, at least for a wide class of parameters containing the average treatment effect and other important effects. So therefore, first observation is that exam is no worse than RCT in terms of the set of parameters unbiasedly estimable with each experimental design. Then one consequence of this result is that exam allows the experimenter to unbiasedly estimate the average treatment effect, right? Because the average treatment effect is known to be unbiasedly estimable with the usual RCT. Then why is it the case that exam can unbiasedly estimate the average treatment effect? The simplest possible answer is that at the end of the day, exam is just a particular stratified experiment, stratified on observable characteristics, especially the willingness to pay W and the predicted effects E. So in exam, treatment assignment is not based on a coin toss, but rather based on some utility maximization problem, right? But imagine that, say, I and Max share the same values of willingness to pay W and predicted effects E. Then the two of us will face the same constraint utility maximization in exam, so that the two of us will get the same vector of treatment assignment probabilities at the end of the day, right? So therefore, as long as some sort of two persons or two subjects share the same value of W and E, the resulting treatment assignment is going to be conditionally randomly assigned and conditionally independent from anything else. So therefore, by the classic propensity score logic, the same conditional independence holds, conditional on the vector of treatment assignment probabilities or propensity score as well. Then this observation motivates, a variety of possible estimators of the average treatment effect using exam data. So one possible way to go is just this one. That is, as a first step, let's focus on a subsample of experimental subjects, who share the same value of the treatment assignment probabilities. Then let's regress the observed outcome yi on observed treatment assignments dit to get these coefficients beta pts. And this beta pt is an unbiased estimator of the conditional average treatment effect of each treatment t on the final outcome for this subpopulation of individuals with a specific value of the treatment assignment probability. Then to move from these conditional average treatment effects to the unconditional and global average treatment effect, it only remains to take a particular weighted average of these coefficients. So for example, if we weight these beta PTs based on the population fraction of each subsample relative to the total number of experimental subjects n, then the resulting weighted average of beta PTs turns out to be an unbiased estimator for the average treatment effect. So by using this estimator or other similar estimators, it's possible to estimate the average treatment effect and other key treatment effects using exams data. Then this is a point about bias. And in the paper, I also provide some discussions about variance as well. And one observation is that even in terms of variance, it is not necessarily the case that exam is worse than RCT. And in fact, so there are certain situations where exam's average treatment effect estimator is more precise than RCT's usual average treatment effect estimator. But in general, the variance comparison between exam and RCT remains ambiguous and remains to be an empirical question. So in the last few minutes,
Yusuke, just a quick, there's a question from the audience. Sarah, would you like to ask your question?
Let's see.
I could hold it till Q&A. It's probably less clarifying than just a question.
Okay, sure.
Oh, yes. So then let me answer this question.
Okay.
Then in the empirical application, I use data from a water source protection experiment done in Kenya a little while ago. And this experiment, fits into my framework as follows. That is, experimental subjects are about 1,500 households in the original experimental sample who are randomly assigned to a binary treatment of the protection of the spring in use at the baseline versus no such protection. So here the protection means that means some cleaning up of unprotected springs on the left, into something like the right one. So the experimental NGO tried to improve the quality of these springs or water sources, to avoid a bunch of bad outcomes such as child diarrhea. So as a primary outcome, I'm going to use the incidence of child diarrhea and the heterogeneous treatment effect of this treatment T1 on this diarrhea outcome corresponds to that E symbol in my model. Then on top of that, an additional piece of data about household water source choices also allows me to estimate households' heterogeneous willingness to pay for this spring protection treatment. So I'm going to use this data to estimate both E and W, then use the estimates to implement exam and compare exam with RCT in terms of important properties. And here is a summary of my findings. So in terms of subject welfare, exam turns out to be substantially better than the RCT. For example, this is the distribution of the welfare measure, the willingness to pay welfare measure on the x-axis, while the y-axis is its cumulative density. And then this dotted blue line is the distribution of welfare and the RCT. Now, what happens if we switch from this to exam? The resulting new distribution is this red solid line. There is some first order stochastic dominance improvement, and the average value indicated by the vertical line improves by about 90%. So exam seems as much welfare better than RCT. Then despite this welfare merit, exam's average treatment effect estimation turns out to be also as unbiased and as precise as RCT's average treatment effect estimation in this particular setting. So here, this blue distribution is the distribution of average treatment effect estimates under RCT. If we switch to exam, the resulting distribution of average treatment effect estimates is this red distribution, which is very similar to the original blue one, right? And the similarity between these two distributions, blue and red, shows the following 2 points. So first of all, both exam and RCT, okay, have very little bias, and both of them allow almost unbiased estimation of the true treatment effect. On top of that, the two designs share very similar standard deviation or standard errors or variance in this average treatment effect estimation. So therefore, if we sort of summarize what I talked about, this experimental market or exam is a solution to the sort of following hybrid problem of mechanism design and experimental design. That is, we'd like to maximize the welfare of experimental subjects, but subject to the constraint that we need to provide as much information and as much incentives for truth telling as in RCT. Then the empirical results from this data about the Kenyan water source protection experiment is consistent with the theoretical result. So we can achieve some welfare improvement at almost no cost in terms of information and incentive. So I'd like to interpret this exam as a potential sort of modification or enrichment of RCT when the experimenter cares a lot about subject welfare. So the final point is that the general takeaway is that economic thinking could potentially contribute to facilitating the advancement and use of complex, adaptive, and other novel clinical trial designs, which is one of the performance goals set by the Food and Drug Administration for 2018 to 2022. And today's discussants have even sort of more clear contributions to this goal. So I'd like to engage in additional discussions about this general point in the Q&A section as well as the breakout room. Thank you so much. I'm going to add just one more modification to the previous definition. That is, starting from the P star thing on the last slide, let's modify it to what I denote by P star of epsilon. Okay, this orange object. This P star of epsilon, okay, is just a mixture of the original P star, okay, and the RCT assignment probability, such that the resulting mix is always bounded between epsilon and 1 minus epsilon for every subject I and for every treatment T. And here, this epsilon is some design parameter, okay, picked by the experimenter as some small constant, such as 5%, maybe 10%. Okay, so given the experimenter's choice of this epsilon parameter, okay, let's compute this P star of epsilon object, which will be the final treatment assignment probability, okay, in this exam, okay, or experimenter's market. Now, if you are confused by this slightly messy definition, then you can take this P star of epsilon or exam as some black box algorithm that will compute assignment probabilities based on your data. But at the very least, I should convince you that this exam is not just a sort of crazy monster that comes from nowhere, but rather a natural extension of the usual RCT to think about. So to clarify this point, let's imagine a situation where the experimenter has no clue about willingness to pay or predicted effect. The very sort of classic scenario, okay, with no information, no additional sort of information about welfare. Then even in this scenario, it's still possible for the experimenter to implement the exam, right? Because the experimenter can simply sort of make both willingness to pay W and predicted effects E be the same and constant for everybody and every treatment. Then in this scenario with no welfare data, okay, exam turns out to reduce to the usual RCT, in the sense that the two experimental design produce all the same assignment probability for everybody and every treatment. So therefore, this exam is a strict enrichment of RCT, okay, developed to incorporate the additional information about willingness to pay and the predicted effect. Then in general, of course, there are millions of possible ways to incorporate the data about willingness to pay and the predicted effects. Then, so why should we use this particular design introduction? And thanks everybody for showing up in this maybe early morning in the East Coast. Then today I'm going to talk about the problem of ethics and the welfare in the design of randomized experiments. So the motivation is very simple. That is needless to explain to this crowd, but now it's the sort of the golden age of RCT or A/B tests, right? That RCT is a social standard of evidence, not just in economics, but also in the whole society, I would say. Then if we look at the real-world implementation of these RCTs, then we are going to immediately notice a couple of very striking features. First of all, these RCTs involve a really big number of individuals as experimental subjects. So I'm going to be specific about a couple of numbers, but looks like hundreds of millions of individuals participate into some RCTs in recent years. Then for such a large population of experimental subjects, many of these RCTs randomize very high-stakes experimental treatments. Say, think about some medical clinical trial where the treatment is a cancer drug or a new HIV prevention drug. These things are literally life-threatening. And now so we are seeing an inflow of lots of RCTs about COVID-19 vaccines as well. Then even in social and economic domains, many RCTs allocate critical treatments such as basic income and health insurance, police patrol, and so on and so on. Then these 2 points jointly mean that what's happening in RCTs influences the lives of numerous individuals. So given this high-stakes nature, what I'm going to try to do today is to provide a design of a randomized experiment that can improve the welfare of participating experimental subjects while producing enough experimental information to do causal inference and impact evaluation. More specifically, I'm going to use a microeconomic model or a mechanism design framework to derive a Pareto optimal stratified experiment, so to speak, with the following 3 features. So first of all, my proposed design has a welfare optimality property in the sense that it creates a Pareto efficient allocation of treatment assignment probabilities, where the experimenter assigns each treatment to subjects predicted to experience better treatment effects or to subjects with stronger preferences for that treatment. For the second preference aspect of subject welfare, the proposed design has also incentive compatibility. That is, it provides subjects with simple incentives to tell the truth about what kind of treatments they really want. Finally, since this is an experimental design, it also should allow the experimenter to estimate or unbiasedly estimate the key causal effects that are usually estimated with data from an RCT. And the proposed design indeed has such a good information property. So I'm going to propose an experimental design with the 3 features, welfare, incentive, and information. Then after developing such an experimental design as a purely theoretical concept, I'm going to also verify and quantify these properties through some empirical illustration. And my empirical analysis is going to be based on data coming from a water cleaning experiment done in Kenya in mid-2000. And through this empirical application, I'm going to find that the proposed design is indeed substantially better than RCTs in terms of these 3 properties. Specifically, it's possible to improve the predicted welfare of experimental subjects while producing almost the same treatment effect estimates with almost the same standard errors or precision. So this project is a mix of some methodological development and an empirical illustration. And it's clearly mission impossible to explain all of these points in 25 minutes. So I'm going to mainly focus on the sort of the conceptual side of this experimental design and provide only a brief summary of the empirical result. Then before jumping into the analysis, let me spend just 1 minute into explaining, why this problem is important and interesting. That is, why should we care about subject welfare? So my answer to this question consists of 2 simple facts. So fact number 1, RCTs enroll hundreds of millions of individuals as experimental subjects. So to be precise, I computed the number of patients who participated into some medical clinical trials from 2007 to 2017 based on WHO's clinical trial registry. Then this analysis or exercise shows that, okay, the total number of clinical trial participants was over 360 million during this decade, okay, which is even larger than the entire US population. And I did the same computation for social and economic RCTs as well, based on the AEA's registry. Then the number turns out to be order of magnitude smaller, but still more than 22 million individuals and households participated into economic experiments. So it's probably fair to say that hundreds of millions of individuals and maybe billions of individuals if we include online A/B tests conducted by web companies and tech companies. Okay, this sort of massive number of individuals are participating in the RCT in recent years. Then for that sort of subject population, many of these RCTs create very high stakes resource allocations. And this high stakes nature is kind of obvious in the case of many medical clinical trials, right? That is, think about COVID-19 vaccine trials or this specific clinical trial where the treatment was a newly developed cholesterol lowering drug. And this drug was randomly assigned to over 4,000 heart disease patients. Then this drug turned out to be a miracle drug, so that